Thanks, Tony. And thanks to the organizer for being here. It's been a great week. So I want to tell you about a long-lasting project that started more than 10 years ago. So I think I'm done, and I'm happy with that. So I want to tell you about possibility for Skein algebras. So I'm not trying to go to the end, so I'll stay different right now. It goes through the Skein algebras. And if you don't know what positive means, so if we take so if you take an algebra over say Z or in Q, then we work with Z over R. Then it says to be positive if there is a basis as a module. Q plus module, such that whenever one multiplies together two of these basis elements, so we get a new element of the algebra. One can expand on the module basis, and that reduces some coefficients. Okay, and we want the coefficient to lie in n of Q plus minus 1 to avoid seeing any minus signs. Okay, so I'll start with explaining the bit between the main theorem, and then I'll try to give you an idea of the proof. And the non-surprising thing is it's based on categorification. Right, so that was having to use this week, I think, or in some of the guys. But what has appeared in Maths code is the Jones polynomial. So if you start with K not in S3 or R3, then a well-known invariant for it is the Jones polynomial, which is an invariant although not indeterminate. And so one of the goals by MTH was to extend that not invariant into a terminable invariant. And so what Mathas feels that one way to go there is to use so now I want to go to a setting where we have K now in some terminable. And Witten, Skein, and Schreier defines some terminable invariant that's based on the Jones polynomial that's by this averaging process. But that requires to take Q a root of all. And so still back in the late 80s, early 90s, Schreier and Stinsky were trying to get some other way to generalize the Jones polynomial to terminals without specializing Q to anything, giving it as a parameter. And so they came up with this module that's Schreier Skein module this one does not require Q to be a opportunity, so we can keep it as a parameter. But on the other hand, for general terminal, we might have option. All right, so I'd rather look at that part of the picture. And so one reason why I care about it is because if one takes the terminal and take a peek at the fitting of it, you look at the surface, some genius surface inside the terminal, you just that, and you get the composition of the terminal into two antibodies. So one gets G and they are glued along the boundary, which is a genius surface. Then that induces some decomposition for the Skein module as well. And so one gets that the Skein module of the terminal is the tensor product of the Skein module of each of the bits. And the tensor product taken over the Skein module of gluing surface. And so in order for this to make sense, this is actually an algebra. And so there's some interesting structure to understand here. All right. So I perhaps give you a more precise definition of what this algebra over here is. And usually I just draw the interval here, so say that the skein of as t is the same as the skein of trinomial. That's what they like the thickened space. I'm using notation. Yeah. All right. So what's the skein algebra of? Okay. We just take the idea is we just take the rules for the polynomial and pretend that we look at nodes of the node diagrams on space and we just apply the local rules that we used to in the data. We take the z cubed plus minus 1 module generated by diagrams of nodes on the space or node on X. Usually unable to do the real thing. So we have these diagrams on the space, and we allow ourselves two kinds of relations. First one is that whenever there is some small disk, small particle that bounds the disk, that can be removed as a cause of I've been mixing my variables. Here one gets minus 18 minus 8 minus 2. And whenever one sees the crossing, that can be transformed into this. So if you have a lesson definition of the polynomials that are based on the Gartner brackets simulations, so exactly what it would be for in the case of the circuit here is just the plane or the physics. All right. So this is for the module structure, but in the case of the algebra, we have one can define a product. And so the way it goes is so I want to multiply two Skein elements. And what one does, one just roll them together on the same cookie of the surface. And I draw the left, so that one on the left hand side first, and then the second one comes under the next one. So I just have to design it. That's one of the how what they use like new plotting. And so when we have such picture, then we mean that origin we can simplify it and then to wish. So I can do that. Here one goes left first, we have that plus a inverse. So it goes that way. So here our first possibility is that I actually two things that might qualify as basic elements. I just multiply them together, and I get Laurent polynomials, which are actually just monomials with non-negative integer coefficients that depend on input curves that might qualify as basic elements. So this really starts well if you just take a slightly more example. Just take two particles of Chebyshev. Then when you draw them together, what comes out is something that has 4 constraints. So for each of them, there are 2 ways to express it. So that comes together to the 4 to 15 then the expansion. And if you try to use computation, you will see that not everything is positive. All right. So before saying the conjecture, I think. Oh, sorry. Yeah. So one thing that that's about the picture is that if we found all of the crossings to be smooth all of the crossings, and then remove all of the trivial components, what we'll be left with is just parallel copies of simple closed curves. So we get a natural basis, which is given by the own multi-curve. So that would look like but this would be a multi-curve. So it's very easy to see that the time is slightly harder to see that they actually in free separation rate also. So just before stating the positive statement, I need to bring some aside or to check polynomials.
But you just said that the multi-curves are not a basis.
No, they are basis.
Right, there's not a positive basis.
Yes. And if you run this example over here, you should be some negative coefficient. Yeah.
So really, the only way that the negative coefficient can follow is because of this relation, right?
Yeah, exactly. The thing is here, I think if you smooth, like here you would have the circle over here. That's not produce minus sign. And I think in that case, you would have another one dropping around as well to the balance, but in some of the other sense, you wouldn't have execution. So somehow the general picture is that we will come to some basis where a lot of constants might have negative signs coming out of this relation, those are copies that they will balance, and at the end of the application, you only have positive coefficients.
Trying to figure out what a multi-curve is.
An embedding of copies of a circle on the space. Yeah. Such that no component is trivial when homology. Right. Alright, so I need an insight on Chebyshev polynomials. And I try to use a 30-second definition, but I think that if I look at the representation ring of representations, I can mostly to the C of S equal to C, and then where X corresponds to that. X corresponds to that of the vector representation. So we have several interesting bases for this ring. One of them is the one related to the n, which corresponds to X to the n. Another one is given by Sn's to SNB. This one I denote to UN, and this is the Chebyshev polynomials of the circumference. And the third one that's representing is Sn minus Sn minus 2. And this one is Cn. And so one way to understand better that if you now replace X by X plus X inverse, we're looking at the weight condition of B, then he gets just X plus X inverse to the n. Then this is the sum of the X to the k of X to the X to the something like X to the n minus 1 plus X to the n minus 3 plus all the way to X to the minus n plus 1. And this one is even simpler you get Cn x to the inverse. This is that one. You just get x to the n minus 1. Okay, so minus inverse. I just in this extension. All right. So now I can see. Yeah, so what we have in there is the algebra basis going each way, and all of these are triangular with positive coefficient going in that direction. So this extends positively on this one, and this one extends positively on that one. All right, so the conjecture that Skein of SD is positive for the basis obtained multi-curves by use of Tn. So somehow, whenever you have parallel copies of the same curve, you want to replace it by the Tn polynomial associated to that simple associated purpose curve. So you take into the very same basis as you have between this basis by the thing that the product of the computation and this one that given method extreme always fit. So this conjecture goes back to Fock and Goncharov, and that has been worked by Thurston and me. And in terms of proofs, the case where SD is the torus goes back to Frohman by Frohman and Gelca in 1999. Then Thurston proved it at right 81 for any surface. Then Busso did LG equals E2 minus a dot, or S3 minus 4 dots. And so I did any ST, but another basis. That's yeah. And finally, I think a couple of weeks ago, actually, a little more than that now, Mendel and Chin proved the full original. So now it should be solid error. So let me tell you about the way I got to this proof.
I would just have a question. What is the second to last one you say? You did the one.
So I do any surface, but I don't take that basis. I just swap the Tn for the QX.
Okay.
For any SD but the torus. And for the torus, it's just wrong for the special basis. But for a very clear reason. For very good reason.
What is your last one? Second.
Mendel and Chin, they did just the full original one.
And totally different things, I guess.
Yeah. So yeah, so if I wanted to advertise why it's so important relation there are two reasons. One is related to this work that all of this is very closely related to cluster algebras. And so there have been a lot of work relating to modules in Skein algebras, algebras, and they care a lot about positivity of finding positive bases in algebras. And so for Mandel and team, they have a slightly different framework because they usually work with extra functions. So they have arcs rather than curves, but so they prove that they can in the context of algebras. The other one is that so I can see that as a heuristic to say that we have the right categorification. So being able to use Khovanov homology typing to prove such a statement, I think tends to show that we have the right constructions for explicit variance in thickened surfaces. So that was meant to be a test that we do have natural constructions. All right. So why? So perhaps I think probably why does classification help with such statement? So if my algebra A has some category input, and if my category is very simple, then whenever I have A1 tensor with A2, so I would like to have a modular product on a category, and I would want to have something to be single. Then this would be imposed into a direct sum of simple objects coming with some input. And then when you go down to the zero, you get that A1 and A2 is as the sum of A size with AI, and because this is supposed to be the dimensions, it cannot be positive. So the hope that using the classification, you might get something about positivity for kind of algebra, and it's an idea that we're powerful in class. We do that, it doesn't work that easily, but the idea is that. So what we need is, first of all, we would like to have some simplification of the Skein algebra, then to have some product on it, or something similar, and then some selective interval. Good. Let's do that. So the categorification part is based on what well understood business. One can use Khovanov homology and all the derivative tools that come with it, and Mathas version of all of that. So one can define a category called Mathas, where objects are so let's say crossing lengths. Yes, I don't want to write multi-code because I want to keep a trivial checkers about and I learned state arithms and growing shit and morphisms. So are probabilisms in S loss interval. So it gets in terms of drawing, it gets a little bit involved. I'm doing my best. So Well, so both of these things are objects. I have the empty curve, or I have this more one. And in between, I can draw a Boston that shows the even version of the torus, mapping from no curve at all to this thing, and say I can choose here curve in kind of K and so imagine that you have the two curves going close to each other, and that's important. Merging together in the curve. Okay, and family relations, which are whenever we see above a Skein that is 0, a torus accounts for 2, and we have this triple relation that whenever we have cylinder, 2 times cylinder equals so we have, the precise meaning, but not that that's important. Just I think it's based on what is in some portion of it. And so this is the original definition going back to Khovanov and Mathas was stated in the case of R2, not in R3 with diagrams on R2, but one can just extend it at no cost to any surface. And so now one has a map that goes from the basic diagram and assign complex by saying that whenever there's a crossing, one should replace that by some piece of complex that looks that way with a salary equals. So there's some elementary local operation that lifts up this Skein operation that we had before, that instead of taking some linear expansion, we just take a complex from we build a complex from the diagram. And so the theorem by says that if you look at whatever it is that you can build from this process, if I look at this in the homology category of like what is the category? This is an invariant, you know. Okay. And furthermore, the K node of the N is exactly my okay, which is saying that we have some categorical lift for the Skein module, and furthermore, we have this special Khovanov map that tells us what to do whenever we have a diagram and how to somehow replace this smoothing ring that we had before. And I should say that the other circle removal rule follows, has a translation in terms of this thing, so it somehow visually. Okay, cool. So it feels like we're almost in business, except that if you remember, we also wanted some kind of simplicity, and here's where it can become complicated. And so our first theorem is Paul, who's called Wedrich. Where that this category ENS admits a non-negative clothing. And furthermore, right, with its degree 0 part being symmetrical. So we have some graded version of symmetry, which should be good enough for us. I won't tell you all this. In the case of the analogous, we should get back to one picture that we before. So what would be nice about it in the other case? So I want to look at it. Things that live in thickened analogous and say insert this one. And add some detail. So what I'm drawing is some kind of positive that goes from one computer station. I think it's a time with some kind of. This has the visual feature that it has some conjecture, which is nice for us, and that's basically the feature that we use. But so what I should ring about that if I take the section of my thickened analysis over here, what I see is that with and what we get to is exactly the Lottie temporary algebra that's appeared in my scope. And it's not negatively rated just because the dot is of two, and so we have in zero, we have the usual temporary algebra plus some higher. So somehow the other case is very easy, and that gives us work with David Rose as well and with suffering. And but she was the first one had to control what happened between different kind of homology. Okay, so well, that's the good news. First one is that we do have some explicitity, and furthermore, the other thing is that we continue. That we know very well what the symbols are over here, and the symbols correspond to John the projectiles. So here, yeah, that provided the survey is not to algebra and interceptor. The value is that if you take a0 of this, what you get is not the Tn basis that would be that was proves positive, only the UN one. But I mean that's how it is. On the torus case, on the other hand, those are not enclosed just because you have one extra piece of origin that goes so if one adds an anomalous in the torus, one thing you can do that wouldn't be allowed in any higher gene scale is that you can take a curve over here and drag it around the torus to come back. And this is degree 0 polynomial, so that gives an extra polynomial just in the torus case that breaks the UN into the TNs. But apart from that case, from the categorical perspective, there is strictly no reason to do the TN, the UN are already categorified symbols, and this is why they should be positive. All right, so let's prove that this one can spectrum multiply positively in Mathas table. Yeah.
The funny conversion goes from 2 circles to 2 circles. The one you just mentioned, I'm sorry.
Oh, it's no, I was just saying, no, it goes from 1 circle to 1 circle.
Okay.
If you take Do you have in mind?
Yeah, I might ask you later, but it's okay.
So what you do is you embed ACL, 30 ACL in the torus, and then you get the graphical one.
I'll think about it.
Okay. We can adjust so if you get this one, then you have the coordinate direction, and the one you want to get is this one. It is the one that is specialized to we choose to compare it with test the polynomial for it, and then you have projectiles and that corresponds to weight based expression. But that's just for the torus. All right, so we are almost there, and it looks like we're almost there. So we had this. So how can we go about in different principal products? So what we want to do is take some curve. So say two curves of one curve, and we want to multiply that with some other curve. So far so good. We know what to do that will go that will be sent to some complex invariant homotopy theory. But the trouble is we're working into the envelope because we have projectiles, and so actually what I want to plug in here is also some so I will run a few things and any drawing attempt, yes, but what you want to plug in is some projectile working that gets superposed with yeah. So you get some mass. The trouble is that you're trying to define. You now have cobordism that are themselves rectangular. So you have a cobordism in the ring category according to links, and one needs to extend Khovanov's contour to this kind of cobordism. So we not only want one of the map from diagrams to compensate, we also want that whenever we have cobordism between link diagrams, that should be sent to some preferred homology between the acidic complexity. And so this is known to fail. It's known that Khovanov homology is not polynomial. It's just projectively polynomial, so there are fine issues. So first reflex would be to say, okay, let's work with each, and there are no fine issues, and we exclude. But then what kind of in the German objects. So I've been looking for any way of we couldn't finding this. And the way to go is to use some fix of this. So they're having fixed by Clark, Morrison, and Walker, Capron, and Blanchet. And so the one I use is Blanchet. And the idea is to replace cobordisms by so-called phones. Phones are singular version of cobordism. The surface technology that when you do the Skein module, a strand corresponds to the vector representation for a set. And in this upgraded version, one should also look at orientation and work with the TH. But then the trend in the other direction that will be the tool, but we have a new player in the game, which now is the two labels arrow that correspond to the sign representation for TH. So suddenly we have webs appearing instead of diagrams of curves, and between webs and natural notion of morphism. You haven't seen that, let's not worry about that. So what Blanchet's theorem gives us is the following. It gives us a functional theory that goes from like link cobordism to complexes multiply on rows. So this is Chebyshev-based homology. So if I take two of my versions of vectors, I can look at that here. So I will have like one of them that I want to multiply with cobordism, and that gets sent to some code. Cool. But now what I want is some kind of product. So I might want to hit that with one more vector. And then I'm in trouble because I know I need to know how to define my Khovanov homology map for phones now. Somehow we've enlarged the target category, but not the source one, but the natural thing to do would be to allow anything that we have added in the target to also be added in the source. So that looks like a slight difference, and so one could. All right. So what we somehow need is some extension of Khovanov's map to phones so that it's defined, but then one needs to prove again functionality for that, and that doesn't follow from Krishna's work. But we can try to prove it, unless for that one needs a presentation of this category, and there wasn't a presentation of this category either. So the first step in that work was to find some presentation for the category by moving moves, and so this is going to work with Kevin Walker on your next step. And so I won't talk at all about that, except that it gives you a presentation by generating relations, and then you're in business to try proving any functionality statement. But the way we've done that is some geometric topology techniques I had never heard about before, or at least never used before, based on Tom's functionality theorems. And I mean, I've learned a lot with working with these things. Only GL2, yeah. No, sorry, no, that's for any flow, any GLN flow. Yeah. But then, right, well, then I just extract the GL2 part by not considering anything with this 6 landing point. And so now from there, in the GLN case, we extract just GL2 piece of data. And then one can go about proving this operator statement. Right, so we got one of homology advance to angles to the homology theory of those. Okay, cool. The proof is a nightmare. You can ask Michel or Daniel about such proofs, and say I've done very similar ones. It's just extremely long. But it's not that difficult.
Is defined topologically or
diagrammatically, but that relies on this, that we return the topological version, topological definition in a diagrammatic one. Some of the content of this theorem is that you can describe this category by diagrammatic generators and relations. And so then you can do some query. So we have a big list of moving moves that control isotopes of phones. I think I have a few minutes. Okay, so we're almost done, except that we run into the problem that Vanessa had earlier this week. That here I have some homotopy category and here not. And so if I ever want to define monolithic structure on the same category, something that takes 2 elements in my category and returns just one in the very same category, well, we again have some trouble, and all we get, if I break these complexes of the commutative, well, we get some kind of bicomplex over here, and making that into just a single complex doesn't work, or at least I don't know how to make it work. But it's not so bad for just the purpose that we are after. Because all I'm wanting is that whenever I take gamma 1 with the tensor, and I want to multiply this with gamma 2 with it, I want to do un of gamma 1 and multiply this by L 2. What I want to be able to do is lift that to some product of gamma 1 J1 gamma 2 J2. And I don't care that much. It's not a unique lifting. All I want to say is that I can lift it up in some way. That's going to expand as the direction of symbol, and then I can just verify. Okay. And the last one we have to address is that in all of this upgraded things to the homotopy category. So by doing so, we get new signs which are bad for positivity. And so this positivity conjecture we formulate to have here, what I want to have here is something that's in the earth to contrary to them, not social but the statement. I think these are complexes that are in the earth from the T structure. So more in the more down to earth version, what we want here are linear complexes, meaning that we want that anything that sits in homological degree K should be made of simples having quantum shift minus K. So that when we get verified, what we get is something like -1 to the K because of the homological one. And for some reason that I won't spend too much time talking about, we get -q rather than q, and then you have the power of K taking the kind of rebalance it produces. So all it remains to show that whenever I take two of the simple elements, they will expand positively in terms of, they can expand in terms of linear complex. And so I just write maybe a trick here just before stopping. There is something magic about the purification thing that so I have gamma 1, say 1, I want to tensor with gamma 2, and prove that this expands as a linear. I want to prove that this is linear. One question that is way easier than gamma 1 and gamma 2 with no reference to the particles is linear. And categorically, this one implies this one, just because this one sits as a direct sum in this one. So if this one expands in some terms, then any direct sum will be in the as well. But what we're saying, so I've spent time wondering if this all the theories are proof actually might work in the original setting without any reference to categorification. And this is why it failed. So if you have what you're saying is you're trying to say that A times B you want to know if this is positive, and you say, well, this actually, what you can say is A times B plus C, this is positive. This doesn't imply at all that A times B should be positive. But as a categorical level, it does. So that simplifies quite a lot of proof, and then we just reduce further with some kind of weaker creativity about when you have this one to be just simple question, and then it's actually just these arguments by computation. Thanks.